Good morning, everyone. So today we wrap up the topic of representation learning. The three subtopics we will look at are distributed representations, and a minor subtopic is exponential gains due to depth. And finally, how we can get some cues on causality. All right, those are three topics. So in the topic of distributed representations, it's a bit of a theoretical topic, but it's a very important one. It brings home the point, what is the mathematical advantage of representing concepts uh, by dividing it up over a large number of elements. Think about it, that's what the brain does. In the brain, the different concepts, like a concept of a dog. There isn't a neuron dedicated to dogs and a neuron dedicated to cats. That would be a symbolic representation. In a distributed representation, the concept is distributed over a whole bunch of neurons. So the concept of a dog and the concept of a cat may have some commonality. It might have many neurons that hold the same information, and together they are holding these concepts. And there is enough proof for this also. Those who have worked with the brain are able to say that if you dissect the brain, a small piece of it is taken out and the concept still remains. It's not like the concept of a dog will be gone. So distributed representation is like that. It's representation spread over many elements. And if you think about it, the elements in a neural network would be all the neurons. So essentially the hidden neurons. Input is a raw image or raw text. And the representation would be a whole bunch of values. These are the latent values or latent variable values, which could be over several layers. Together, they are constituting the concept. So that is what we explore here in distributed representation. We look at a very simple neural network with 2 input units, 3 hidden units, 1 output unit. In the simple model, it's taken from a student's lifestyle. The 2 inputs could be the number of hours studied and the number of hours slept. And the hidden units capture some information from these. And the final output is the score the student receives in the exam. So what are the hidden unit values that comes out of this? And so rather than hold these concepts discretely, they're kind of distributed over the 3 elements. So we'll look at that example and see what is the number of parameters in this model and how they divide up the space into different values, space of the feature values. And then we'll argue that a distributed representation is very efficient, that given a certain number of latent variables, you get a lot more for your money, in the sense that it gives you a huge number of partitions of the feature space. A symbolic representation, on the other hand, would need as many concepts as symbols as a number of different concepts we have. So for each, as I mentioned earlier on, dog, cat, and so on, you would need a symbolic representation for each, whereas a distributed representation does something which allows it to have a more efficient representation of concept. We'll see this explicitly by looking at the equations. And so after contrasting symbolic and distributed representations, we'll look at some practical examples. how these distributed representations can probably be causal concepts. Then we go on to mm, some theoretical issues about the gains that are obtained by having distributed representations. How depth is a very powerful concept. So deep learning is an appropriate uh, title for this type of thinking. All right, let me share my slides right now. Okay, there we are. So we are covering distributed representations, and the slides indicate what the topics are. So this is topic number 4 within representation learning. Just as a reminder, the topics we covered were greedy layer-wise unsupervised pre-training, where we train them layer by layer, and what is meant by transfer learning, how concepts learned when one task can be moved over to another task, which also has some theoretical implications. And we looked at semi-supervised disentangling of causal factors. And today it's distributed representation as well as exponential gains from depth and providing clues to discover underlying causes. So let's begin with this fairly straightforward topic of distributed representation. Within distributed representation, we have these subtopics. And the first one is that neural networks are indeed based on distributed representations. And we contrast that with non-distributed representations or symbolic representations. And then move on to similarity induced by distributed representation. There is an inherent similarity. And then we talk about dealing with the curse of dimensionality. The reason distributed representations win over symbolic representation is as the number of dimensions increase, symbolic representations suffer from the curse of dimensionality. Everything is exponential. And after that, we move on to capacity of a distributed representation. Now, that's an interesting theoretical concept. And how it relates to efficiency. And look at one example of experimental validation of concepts. That is, can we show faces of people and learn the underlying factors, which is whether people are wearing glasses or not, or the people are male or female, and how these kinds of uh, causal factors play a role in distributed representation. And finally, look at a distributed representation that disentangles causal factors. All right, as I mentioned before, distributed representations of concepts are representations composed of many elements that can be set separately from each other. All right, so many elements together define the concept. And they are a powerful tool for representation learning. And they're powerful because we can use n features think of it as hidden values with k values each to describe k to the n different concepts. So we have some linear number n of features and k values we each. From that we get exponentiality, k to the power of n different concepts. So we get a dramatic increase in the number of concepts with a small number of features or neurons or latent variables. So there is a connection between distributed representations and causal factors. So strategy of distributed representation is used by neural networks with multiple hidden units. They're also used by probabilistic models with multiple latent variables. So not only neural networks, but also graphical models with latent variables. So that is known. And we introduce an additional observation that hidden units can learn to represent causal factors that explain the data. So the hidden units contain the factors that explain the data. And distributed representations are natural for this approach, since each direction and representation space can correspond to the value of a different underlying configuration variable. So we're talking about vector representations. A hidden units form a vector. So in that vector, the directions can correspond to the different causal factors. All right, let's see how a distributed representation divides up an input space. A distributed representation essentially breaks up the input space into regions. So this is a simple example. Supposing we had three hidden units, H1, H2, and H3, and each of them is binary. So given an input, H1, H2, and H3 fire, and each fires it into 0 or 1. So it means it's a linear transformation into one or the other. Basically, each feature divides, in this case, in this example, we have a two-dimensional space, or R2, into two half planes. And so we are calling it as HI plus with a set of inputs for which HI equal to 1, and similarly HI minus, and there is the decision boundary. And you can see there are three lines here in this diagram. Three lines corresponding to H1, H2, and H3. Each of them has a positive side and a negative side. So if you look at all the regions, there are several regions that they define. In this case, we can see 1, 2, 3, 4, 5, 6, 7 regions. Actually, it's the order of 9 regions because 3 of them are sharing one region here. So in general, we can say that those 3 hidden units are defining a much larger number of regions. So let's put it into a closer perspective. Here is a neural network that uses a distributed representation. This neural network has 2 inputs, 3 hidden units, and 1 output. In general, we say D inputs. In this case, D equal to 2. And we have n binary latent features corresponding to these. And we say, okay, in this case, n equal to 3. And in this case, we are defining that as being thresholded by this function, which is a sigmoid function, which has got this shape shown below here. That's a sigmoid function, which goes between 0 and 1. So we take these 2 inputs, and each unit goes to either positive or negative. So it's got a positive side and a negative side. And the input to it is a linear function of the inputs. All right? It's of the form W11x1 and W12x2. And we add that up, and then we're subjecting it. So basically, we are defining, each of them defines a straight line. Each of these 3 units define a straight line. And once again, the outputs here are weighted by a new set of weights here. The sum of it is subjected to one more sigmoid function, which takes on the value of 1 or 0. And so it's basically going to be 1 or 0 for each of these regions. And it's a linear combination of these three inputs. So depending on the input, one of these regions is going to be 1 and the other region 0. Because we could say because the input falls in that region, it's going to be 1 or 0. So this is basically what a neural network does, and it is using a distributed representation that the concept is distributed over those three hidden units. So we can attach some numbers to this. So we can say we have D inputs, we have n binary latent features or hidden units, and each feature divides input space RD, that's a d-dimensional space, into a pair of half spaces, right? With a plane that divides into two parts. And one can show that the number of regions created by the intersection of a set of n hyperplanes, right? That's what we have, n binary latent features, can be described. The number of regions distinguished can be written as j equal to 0 to d summation n choose j, and that has a simple expression, which is n to the power of d. Oh, that's neat. Which simply says how many binary features do you have, which is n, to the power of how many inputs do you have, d. In this case, d equal to 2, n equal to 3. This says the number of regions you get is of the order of n to the power of d, or 9. In this case, we saw we already have 7 regions here. It's actually order of 9. And we can also compare it to nd, which is the number of binary features times the number of inputs. So the growth, the number of regions we get with a distributed representation is exponential in input size d. We are getting n to the power of d. We say it's exponential in input size d, and it is polynomial in the number of features n, number of binary features n. With 3 features, then we get some polynomial in terms of that n. With order nd parameters, so if we need 6 parameters to define d hidden units with n hidden units with d inputs. So we'd have order nd parameters. We can represent order n to the d regions in input space. So we get an exponential number of possible regions. So we can get a number of concepts with a small number of parameters. Here we are comparing distributed and non-distributed representations. So a learning algorithm based on a distributed representation breaks up the input space into regions, which is what we just saw, which is what is seen here. Now we are going to compare it with a non-distributed representation. A simple concept of a non-distributed representation is a nearest neighbor. That is, we have 3, let's say in this example, we have 3 concepts. So every concept holds its own in space. So until we move to another concept. So here, this is a non-distributed representation. Each node corresponds to a concept. And we say anything falling in this region is close to this one, anything falling in this region close to this. So these are actually perpendicular bisectors of the line joining these centers. We refer to this as a nearest neighbor classifier, which is a non-distributed or symbolic representation. Advantage of it is given enough parameters, it can fit the training set well without solving a difficult optimization problem. How to figure out a distributed representation is complicated because we need to set up a loss function, and we need to backpropagate to figure out the exact parameters and so on. That's what is needed to figure out a distributed representation. A symbolic representation is extremely straightforward. You simply store all these examples and no optimization. And we use the idea of smoothness or nearness. And the disadvantage of it is that it generalizes only locally via a smoothness prior, making it difficult to learn a complicated function with more peaks and troughs than available number of examples. We might have each example may not be just one. There might be more than one sample, and there might be some variations of those samples. Such as, for instance, if the concept is uppercase A and lowercase a, they're quite different shapes. So they don't have the same shape representation. So how do you represent uppercase A, lowercase a? In which case you divide up the region for A to two parts and more subparts and so on. All that gets extremely complicated with a symbolic representation. So we already said that the number of regions we get with a distributed representation is n to the power of d, where n is the number of hidden units and d is the number of inputs. So what does it correspond to in the symbolic representation? To specify order n to the d regions, because that's what the distributed one is doing, we would require order n to the d examples. And so it says if you want that many regions, you would have to have that many samples. Whereas the first one is saying that number of parameters needed is much smaller. So fewer parameters means fewer samples needed. That's a general rule in pattern recognition, that the number of samples you need is at least of the order of the number of parameters. And the number of parameters needed is much larger for a very complicated concept, set of concepts with a symbolic representation, much easier with a distributed representation. So what are some non-distributed representations? It turns out, like all the classic methods of pattern recognition and machine learning, the old methods, they're all symbolic representation methods. They're not distributed. Like clustering methods, including k-means clustering, or k-nearest neighbor classifier, or the idea of a decision tree, or the idea of a Gaussian mixture model, or a kernel machine such as an SVM with a Gaussian kernel, and also language or translation models based on n-grams. All of these classic methods are all symbolic representations, and we've just been arguing that how these neural network based methods are more powerful than any of these symbolic methods from the point of view of complexity, from the point of view of samples needed. Complexity, I mean, how fine-grained a feature space division do you need? All of that can be achieved with distributed representations, that the symbolic representations will need an exponential number of parameters to achieve that complexity. So that's the beauty of this deep learning approach. One more thing is there's a linear relationship in non-distributed. For some of these non-distributed algorithms, output is not constant by parts, but instead interpolates between neighboring regions. So we talked about the nearness, and we asking for interpolation, which is the closest one, and then we apply that. So that's the interpolation. And the relationship between the number of parameters and the number of regions they can define remains linear. So we already said this, that you will need more and more samples if you're going to have finer and fine-grained differences between different examples. All right, then we'll move on to the similarity concept of distributed representation. In a symbolic representation, this is the example of cat and dog. If you have a classifier, many of these contests they have for neural networks have many classes, including animals, cats and dogs and so on. And in a symbolic representation, a cat and a dog are as far from each other as any other two symbols. say a ship and a bicycle and a cat and a dog, they're all equally far apart in some symbolic space. In a distributed representation, there is a generalization due to shared attributes between concepts. So things about cats generalized to dogs, right? So entry has fur or has number of legs would have the same value. Maybe cat and dog comes across as having features such as has fur or number of legs is 4. So these concepts are induced by the hidden layers. So distributed representations induce a rich similarity space. Semantically close concepts are close in distance. And a property that is absent in purely symbolic representation. So a symbolic representation, this just like dedicating the brain. This neuron is about ships, and this neuron is about dogs, and this neuron is about cats. Every one of them would be equally dissimilar to each other. And where a distributed representation is dividing up the concept into several neurons, is a shared concept, and together they end up defining the concept you want. So what is the statistical advantage of using a distributed representation? Is that when a complicated structure is to be compactly represented by a small number of parameters. Although we struggle with a large number of weights in a neural network, that is nothing compared to the kinds of concepts we're trying to capture. So it's with a small number of those weights, we can capture very complex concepts. This slide is about the issue of symbolic algorithms and dimensionality. We say that symbolic algorithms suffer from the curse of dimensionality. And what is it about? So let's see. Symbolic algorithms assume smoothness. If U is approximately equal to V, let's say U and V are cat and dog images, learned F has a property F of U equal to F of F is the neural network that maps into cat or dog or animal. So if U is equal to V, then F of U is equal to F of V approximately. If F of X equal to Y, we choose approximately equal to Y, we choose F that changes little over the input X plus epsilon. So we have a smoothness issue here in symbolic algorithms. And this suffers from the curse of dimensionality in that the number of examples needed is as large as the number of regions, and each region is a category or a symbol, and a separate degree of freedom is associated with each symbol. Although we can learn an arbitrary mapping from symbol to value, there are no generalization to new symbols or new regions. Again, the same point about having as many samples as regions and the smoothness idea. And that becomes extremely large as the number of dimensions you have in the input. If lucky, regularity in F besides smoothness. So it is also possible that there are some regularities in the function besides smoothness. And there are some examples of CNN with max pooling, which have the main variance. So the main point of this slide is that the methods are prone because the number of subdivisions goes up with dimensionality. And this is what is being stated here. If the input dimensionality is high, the number of regions are going to be very high, and you need more samples. Okay, we transition here into the idea of a capacity of a distributed representation. This is worth paying attention to. So what is the capacity of a classifier? We have an algorithm to classify it into one or the other. So what is the capacity of the method you're using? How do we measure that? We say here that the distributed representation can generalize well because the capacity remains limited despite being able to encode so many regions. So what is capacity then? There is a definition of capacity known as the VC dimension, named after two Russian mathematicians, Vapnik and Chernovenkius. It's called the VC dimension. So of a model F, if you have a particular model, a classifier, let's say, what is its capacity? So it is actually the maximum number of points that can be arranged so that F shatters them. Shatters them means if I give you some number of points, uh, does your method allow you to define the space? Let's say we consider a linear classifier. These diagrams shown here correspond to a linear classifier. It's a two-dimensional space. If I give you 3 points, plus and 2 minuses, I can always draw a line separating these two red minuses from the plus. Okay, yeah, we can shatter 3 points, we say. If the points were these two were plus and this is a minus, yes, we can draw the line like this, it will shatter it. If all these three were red, I can still draw this line. So all these three fall here. So we are saying 3 points can be shattered by a linear classifier in two-dimensional space. What about 4 points in two-dimensional space? So if I give you 4 points and label these two as plus and these two as minus, a single line cannot separate the reds from the blues. We need 2 lines. So we say 4 points cannot be separated by a linear classifier. So the maximum number of points that can be separated by a linear classifier can now be said in RD, in d-dimensional space, is d plus 1. In this two-dimensional space, we can shatter 2 plus 1, which is equal to 3 points. So we say the VC dimension of a linear classifier in RD, d-dimensional space, is d plus 1. So we say that is the capacity if you're going to be using classifier. So we can say that is the kind of classifier you're using whose capacity is limited to d plus 1. What about the VC dimension of a distributed representation with W weights? Well, we can show that it is of the order of W log W, which is the number of weights times the logarithm of the number of weights. So it's of the order of the number of weights. So you multiply it by logarithm of W, which is not that much. So it says the ability to shatter them by a distributed representation is of the order of the weights. So the VC dimension, we say, of a distributed representation is only W log W. So it says we have this limitation because while we can assign many unique codes to representation space, we cannot use all of code space, nor learn an arbitrary function mapping from the representation space H to Y using a linear classifier. So this is an explanation of why it is limited to order of W or a W log W. And a distributed representation to learn H combined with a linear classifier to determine Y expresses belief that classes are linearly separable of the underlying causal factors captured by H. So the limitation comes about because the final classifier you have is still linear, right? And so it doesn't allow for anything arbitrary. And we have a set of causal factors separated out. So we say that a distributed representation has a limited capacity, but still is able to get a large number of regions. And why do we insist on linear classification in a distributed representation? If you recall, the last step in a deep learning network is usually softmax, which is linear. This is similar to how we human beings do things. we typically want to learn concepts that are fairly simple. We don't want a nonlinear classification at the final stage. Set of all green objects or set of all cars. But not categories that require nonlinear exclusive OR, such as a set of all red cars and green trucks as one class, and set of all green cars and red trucks as another class. This is the idea of exclusive OR. We're using 1 and 0 for two variables. One is red and green is the color, the other one is car and truck is the other category. So when you have two binary variables, x and y, there are so many functions we can define with their and or their negations and it or the or of them. And the most complicated of these is exclusive or of them, 1, 0 or 0, 1. And that would be a non-linear operation. So we bring it to a linear operation in these methods. Okay. All right. So anyway, all of this has been somewhat theoretical. So you need to go through them to get a feel for what is happening in distributed representation as opposed to symbolic representation and what advantages we get out of it. Because that really puts into perspective the old methods of pattern recognition and machine learning with the current methods, which is neural networks. What are the main differences is captured by all of these ideas. Anyway, so it's an important topic. So now let's see, ideas discussed so far have been experimentally validated. Hidden units in a deep convolutional neural network have been trained on ImageNet and places benchmark data sets. And they learn features that are interpretable corresponding to a label that humans would assign. So they took examples and tried to look at the representations and what they mean. The hidden units learn interpretable features. Not always that hidden units learn something with a linguistic name. That's an interesting concept. You're trying to develop a neural network to do a classification problem, and then you're asking, what did you learn? And quite often they learn concepts that you would say, oh, that's intuitive. I can understand what you're doing. But they might also learn things that you never expected. And these emerge near the top levels of deep networks. They tend to be concepts we could learn about each without having to see configurations of all the others. So these are not concepts that kind of depend on all the others. They stand alone. Like you're looking at pictures of faces and you are able to learn the concept, they are wearing glasses. It's not like a complicated composition that they're wearing glasses and they have dark hair, what have you, right? So it is just standalone concept. And these are the kinds of concepts that can be obtained. And these are some pictures obtained from a particular experimental work. They had a generative model for faces. So in a generative model, we are not doing supervised learning, or it could be supervised learning, where we are generating a model from which you can generate samples. A generative model that has learned a distributed representation with directions capturing the underlying factors of variation. So this was just fed with large numbers of faces. And this model disentangles the concepts of person is a male, or person is a female, or person is wearing glasses, or person is not wearing glasses. And they learned causal factors. One direction in representation space is gender, male or female. Another is whether wearing glasses or no glasses. And these features were discovered automatically and not discovered a priori. No need to have labels for hidden units. And you're examining what is this node learning. All right, so this is the causal factors that are learned. And this is an interesting observation. They disentangle gender and glasses. It's not a mixture of the two. We've got two independent features here. Using that, we can kind of synthesize objects. Begin with representation of a concept of a man with glasses. Then subtract the vector representing a concept of a man without glasses. And finally, add a vector representing concept of a woman without glasses. We obtain a vector representing concept of a woman with glasses. So we are just dealing with vector representations here. And we can manipulate these vectors to generate samples with these concepts. So generative model correctly decodes all these representation vectors to images that may be recognized as belonging to the correct class. Okay, so that is this first of our three topics today. This is about distributed representation. And let's continue with the others before we close. So we will go into gains from depth. Okay, so this is again an interesting issue, that a distributed representation involving a deep network brings you exponential gains from depth. What we're talking about is how, when we add layers, we don't gain simply in a linear way. We gain in an exponential way, which sounds very powerful. So exponential gains from depth. So what are we going to look at here? We will look at the efficiency of multi-layer perceptrons, and then the expressive power of deep networks, and then the minimum depth required. Yeah, how much depth do you need? And we look at the expressive power. When we talk about expressive power, it means we are talking about, can you distinguish a fine variation, like a particular dog called the Siberian Husky and a polar bear? Maybe they look very similar. They both have white fur and the same type of look. And an ordinary method may not work well when you have a fine distinction you need to make. And that would mean the particular network has to have a strong expressive power. You can say that is different from this, which means you're dividing up the feature space in a complicated way. So on this exponential depth topic, we recall two theoretical underpinnings of deep learning. First is multi-layer perceptrons are universal approximators. Okay, that's a nice theoretical result. It says we can approximate most functions given enough hidden units up to any non-zero tolerance. So this is saying you can, as long as you give me some hidden units, that is, maybe in one layer or two layers, I can give you any function you want. That is, whatever fine discrimination you want between people or between animals and so on. I can give you a good function for doing that. And however accurate you want it to be, I can make it. Wow, you can do that with a network. But there is also a counterpoint that there exist families of functions which can be approximated efficiently with depth greater than d, but which require a much larger model if depth less than or equal to d, which is kind of a nice statement, which is saying, well, I can give you a function, or I can give you a neural network to solve that problem. But if you're going to limit me to the depth of the network, then the efficiency is not going to be good. It will be approximated efficiently with depth greater than d, but which require a huge model. When we say efficiency, how many parameters would you need? How much learning do you have to do to learn those parameters? In many cases, number of hidden units required by the shallow model is exponential in n, right? Is exponential. So we have the exponential factor coming in. So the argument here is deep learning is more efficient than shallow learning. So if I give you a one-layer neural network versus a multi-layer neural network, this is saying that the deep one is more efficient. And how do you argue that? Results for multi-layer perceptrons. That's a standard neural network, feed-forward network. The functions are represented by smaller deep networks compared to shallow networks. So we're talking about deep networks versus shallow networks. So in the sense, the number of units needed in these deep networks is not a large number of units. Number of linear regions with the D inputs, depth L and N units per hidden layer is exponential L. So it says the regions you get in that space, that is the expressibility, is exponential L. And decreasing.
Sir, showing the new presentation, sir.
Go ahead, Setu, tell me.
The next presentation you have not displayed. It's still in the old presentation only.
Oh, is that right? Okay, okay. Oh, I'm sorry. This was a very interesting presentation.
No problem.
And I kind of moved on. And let me, okay, this is, yeah, I need to go to sharing. New share, okay, new share. And okay, that's the one. Are you able to see it now?
Yes, sir. Thank you,
Okay.
sir.
All right. I'm sorry because I went over some very interesting slides here.
Yes, these slides are very interesting. That's why I was just listening to it.
Yeah, this is very, very interesting.
Slides were there because we were talking about some equations and also I just.
Yeah.
Okay.
So that's very good. Thank you for bringing that to my attention. And these were the slides I went over, theoretical underpinnings.
Yes, sir, that's fine, sir. You can just continue, no problem.
I can continue. There's not that many slides in this particular section.
Yes, sir. Only 9
Around
slides.
9 slides here. So, but these are extremely important from a conceptual understanding of deep learning. That's why I think it's very worthwhile.
Correct, sir.
Right? How many regions can you get out of a deep network? How a deep network is actually more efficient than a shallow network, as long as you're able to give me the number of units needed. A shallow network will require a very large number of units, whereas a deep network, is not exponential. That's where the exponential gain comes into the picture. I think that's the last slide here almost. Oh, no, okay, there's some more. Size of H for universal approximators. So this is about, well, okay, single layer is enough. That's a universal approximator, but how big does it have to be? Look at the bottom line, it says no, required number of hidden units, H is large. So these are all arguments here. So composition of nonlinearities and hierarchy of reuse features can give exponential boost to statistical efficiency on top of exponential boost given by distributed representation. So if you have complicated models, these were actually theoretical results shown for more complicated functions. Many networks with nonlinearities, Boolean gates, some products or radial basis functions with a single hidden layer are universal approximators. Okay, those networks can get you any function you want. But a model that's a universal approximator can approximate a large class of functions up to any non-zero tolerance given enough hidden units. If you give enough hidden units, they can give you the function to whatever accuracy you want. However, the required number of units is large. So the expressive power of deep networks is that there are families of functions that can be efficiently represented by architecture of depth k, but would require an exponential number of hidden units with insufficient depth 2 or depth k minus 1. So this is saying that you can use a certain depth, but the number of units required is going to become exponential. What about minimum depth required? So all of this is invoking theoretical type of work here, but these become useful to have an idea. We can say experimentally, I'm going to use 3 layers, 4 layers, 5 layers, whatever the computational power you have. But they have shown some results using other networks called sum product network, which use something called polynomial circuits. And these model a probability distribution over a set of variables, and showed that there exist probability distributions for which a minimum depth is required to avoid needing an exponentially large model. So they have said that you're going to need a certain depth, otherwise you're going to need an exponentially large model, is the guidance that's been done. And this has also been worked upon for convolutional neural networks. And argument there is an exponential advantage of the deep circuit, even when the shallow circuit is allowed to only approximate the function computed by the deep circuit. So they played around with saying, let's do an approximate CNN for this problem. And they're saying there's an advantage for deep networks to do better than these, right? Just like many theoretical results in algorithms, here again, these are just indicative. And we haven't really arrived at a formula saying, okay, I'm going to do cats and dogs. Should I have 3 layers or should I have 13 layers, right? There is no guidance being given here. But it is just saying that the advantage of a deep network is, uh, is there for a shallow network, particularly for complicated concepts you're trying to learn. If you're going to be doing very complicated classification where things have fine-grained differences, like a particular type of dog and a particular type of wild animal, there's only small difference. What does it take? Well, for that kind of a difference, you need a high variability partitioning of the feature space. So it says you are better off using a deeper network for that than using a shallow network for doing that. Whereas for a problem that doesn't involve such fine-grained distinction, maybe a shallow network will do. All right. So this is the kind of guidance, and we always look for the theoretical work to see what can you tell us. All right. I got one more set of slides, and let me see if I can follow the discipline of sharing that properly. First thing, I got to find that slides, then I have to share it with you all. Okay. So this is going to be on the clues, which is 15.6, I think. Underlying causes. Okay, I'm going to now share this with you all. New share. 15.6. Share. Okay. So, Selvi, can you see this new slides?
Yes, sir. Thank
Okay.
you, sir.
Okay. All right. Thanks for being the only person giving me some feedback. All right. Okay. So this one is providing clues to discover underlying causes. This promises a lot. Saying, wow, you can give me clues as how do I discover that these photographs, some people wear glasses, some people are male and female. Can you give me some clues? How should my network discover these concepts? This says there's a whole variety of things you could try out. And again, it's just potential for doing all this. And we're going to conclude by saying this is a very good topic for research. All right, let's see. Providing clues to discover underlying causes. Like the particular image you're seeing is like this because this person is a female and this person is wearing glasses, which is why you're seeing this image. So those are underlying causes. And can the network actually give you an answer like that? All right. So what are the topics in clues to causes? So first of all, again, we revisit what is an ideal representation. This being the last part of our representation chapter, we have to conclude by talking about what is an ideal representation and what are the clues to find factors of variation. And we talk about generic regularization strategies. So these are like very generic, but anyone could use them, not for a particular task. And just as the word regularization reminds you, when we studied the early part of machine learning or deep learning, we talked about regularization strategies and we talked about there are a dozen or more regularization methods, such as the norm penalty, right? And early stopping and dropout function and so on. There are several methods for regularization. Just like that, in the process of learning proper representations, we can also have some influences. Just like in the other area, regularization means giving some prior knowledge. Same kind of thing applies here also. And then we conclude by saying, what's the summary of representation learning? So again, we begin by saying, what makes a representation better than another? Keep in mind, in deep learning, the features are all being learned. This is unlike standard pattern recognition or standard machine learning, where features are engineered by a human being, saying, well, to recognize a cat, I'm going to write a piece of code that recognizes ears, recognizes legs, and so on. No, no. In deep learning, all those are being learned by the system. So it is learning a representation. So we are now asking the question, what kind of representation should it learn? So it says an ideal representation disentangles underlying causal factors of variation that generated the data, especially those relevant to the application, right? So it learns the causal factors of variation, right? You're trying to recognize people, maybe glasses helps and male, female helps and so on for that application. And most strategies introduce clues that help the learning to find the underlying factors of variation. So we say in the learning process, we need to introduce some clues. And clues to find the factors of variation. Well, one major clue is if the problem is supervised learning, then that itself is a clue. Supervised learning provides a strong clue. Label Y presented with each X specifies one factor of variation directly. So you're saying, well, you know, if I give you that this is a training set and this is the label associated with it, you're giving a clue as the label. But that, so we're talking about it has solved the end problem, but what kind of representation did you get? That clue is the label. To make use of unlabeled data, that's not supervised. Representation learning makes use of other less direct hints about underlying factors, right? So we want to use less direct hints, not simply saying that is the label. And from designers of learning algorithm to guide the learner. So this comes from the learning algorithm designers, just like the supervised label, they have another methods. So the goal of deep learning is to find regularization strategies applicable to many AI tasks that people solve. So what kind of regularization strategies are useful when people start taking AI and applying it to all kinds of problems? what kind of regularization strategies they could use, right? So that's what we're asking. So here are 1 through 11 generic regularization strategies to encourage learning algorithms to discover features that correspond to factors of variation. So what are ways of encouraging a particular learning algorithm to do this? First one is smoothness. Somehow the algorithm or the method should involve smoothness, just like in symbolic representations. The concept of linearity, the concept of multiple explanatory factors, the concept of causal factors, the concept of depth, hierarchical organization of explanatory factors, and then shared factors across tasks, manifolds, the idea of manifolds, being on a manifold, we saw this earlier on, natural clustering of the data, temporal or spatial coherence, sparsity of the models, and simplicity of factor dependencies. So those who have been searching to come up with good generic strategies to discover causal factors. So when we have the network, not only is it finding some hidden representation, the hidden representations are meaningful, and it says use some of these ideas in your design. So a little bit more detail of those 11 factors, 11 clues. So assume f of x plus epsilon times d is approximately is f of x for unit d and small epsilon. So we have uh, when you update x by an epsilon times d. So that is I suppose the dimensionality of the hidden space, and so there is smoothness here. Allows generalizing from training points to nearby points. And many ML algorithms use this idea, but it is insufficient to overcome curse of dimensionality. We just said smoothness is the problem with symbolic methods. Some idea of smoothness may be useful for distributed. Linearity is it assume linear relationship between variables, which allows predictions far from the observed data, but sometimes leads to extreme predictions. The concept of linearity is something that can be used. Multiple explanatory factors is that we are dealing with data is generated by multiple underlying explanatory factors. We are assuming that it's not just one reason, there are several multiple reasons. And learning P of X requires some of the same features that are useful for modeling P of Y given X. X is the input, Y is the output. So just going to all the way to the output has some similarity with going to the intermediate representation. So going in different directions in space. So model treats factors of variation described by H as the causes of X and not vice versa. Okay, causal factor says the hidden units are capturing the causes of the observed X and not vice versa. It is because the person is wearing glasses, you are seeing this image. It is because the person is male, you are seeing this image. That's the causality. As opposed to because you are seeing this person, you are seeing glasses. That would be the anti-causal. So causal factors go from parent to child. And that's why we refer to them as causal factors. Again, this invokes another basic concept of statistics. Causality and correlation are not one and the same. Right? So causality is one direction, whereas correlation is both directions. That whenever this happens, whenever you have a dog, you see four legs, right? Whenever you have four legs, you see dog. So that is correlation. But causality is because it's a dog, you're seeing four legs. So that is directional. So the This is useful for semi-supervised learning. We saw that earlier on. Semi-supervised learning uh, can exploit causal information, where you have the distributions are multimodal, and within a few examples, we can learn what is the distribution for each class when the features are causal. And the learned model is more robust when the distribution over underlying causes changes, and when model is used for a new task. So the depth issue is by using a hierarchy of explanatory factors, high-level concepts defined in terms of simple concepts. So that essentially leads to your dealing with high-level concepts defined in terms of simpler concepts. And another viewpoint is that tasks should be accomplished via a multi-step program. Yeah, we give this analogy of deep learning and algorithms that have several steps. Sometimes you can write a program for a particular task, which does it all in one step. It gets you the answer in one step. There's another algorithm does the same job, but it kind of goes through intermediate steps. Which is better? Well, if they're getting the right answer, they're both equivalent. But the second one is a deeper model, goes one after the other. And there is certain advantages we have talked about. The deeper model can tolerate higher degree of complexity. So we're saying a multi-step program is better than a single-step program to solve a problem. And we're applying that to distributed methods. Each step referring back to the output of the previous processing accomplished via previous steps, right? I suppose this is one of the fundamental concepts in computer science, where we say break up your problem into sub-problems and solve each of them separately, as long as, of course, your overall problem is solved correctly. Another clue is about shared factors across new tasks. So if you have multiple tasks and so each of them can reinforce the other to get the shared cues. And the idea of manifolds, and we talked about this earlier on, probability of mass concentrates in locally connected regions and occupy a tiny volume of the entire space. All the variables define a huge multidimensional space, but your object of interest, the cat or the animal, occupies only a very small part of that space. And these are characterized by low dimensional manifolds. Many ML algorithms behave sensibly only on this volume. So there is the importance of understanding the volume. So if you have something beyond that volume, it might not make sense. Many ML algorithms, especially autoencoders, attempt to explicitly learn the structure of manifolds. So we have to refer back saying, you could use the idea of autoencoders to learn manifolds, which can be useful for the idea of causal representation. Clustering is also useful. Many machine learning algorithms assume that each connected manifold may be assigned to a single class. So we're saying this manifold is cat, this manifold is dog. And they might be disconnected manifolds. And this motivates many learning algorithms, tangent propagation, double backprop, manifold tangent classifier, adversarial training, and so on. So most important explanatory factors are assumed to change slowly with time. So these are not like looking at a few pixels here and there. Those would change dramatically from photo to photo. So there is something broad about the faces you're looking at. It is easier to predict the true underlying explanatory factors than to predict raw observations such as pixel values. So temporal coherence or the spatial coherence. Another clue to causality is sparsity. Most features are not relevant to most inputs, and no need to use a feature that detects elephant trunks when representing an image of a cat, right? So there might be all kinds of feature extractors you might have. And if we have 1,000 class, ISLV, one of those competitions have 1,000 class So there might be elephants and cats and so on. And the features you detect for an elephant will be relevant to cats. So reasonable to impose a prior that any feature that can be interpreted as present or absent should be absent most of the time. So the features uh, are not present over all of them, which means it's kind of useless one. And it's absent most of the time, but specifically for this class, it is present. And simplicity of dependencies, factors related through simple dependency. Simplest is marginal independence. So the probability distribution associated with that hidden vector H is nothing but product over I of P of HI. It says all the hidden units are independent of each other, which means the causal factors are all independent of each other. The joint probability is the product of the marginal probabilities. That's one possible assumption. Actually, that is the idea used in what are called as variational methods. A simple version of it uses this kind of independence. And then there is linear dependency is also reasonable because of many laws of physics and assumed when plugging a linear predictor of factorized prior. So simplicity of factor, that's Occam's razor in some sense. So we come to the last 2-3 slides which summarize our chapter 15, which was all about representation learning. Representation learning ties together all the many forms of deep learning. Feed-forward recurrent networks, autoencoders, deep probabilistic graphical models, they all learn and exploit representations. And learning the best possible representation remains an exciting avenue of research. So we have not given ultimate, absolute, directions here, saying this is exactly what you got to do. We can't even tell you how many layers is the right number. And so we're saying it should be causal, features is good, so on. So saying is an important avenue of research. And here is one representation diagram which shows how we are learning diagonal lines, and a node corresponds to diagonal line in the particular 45-degree direction, and there is a node for that it's a face, and that's a node that it's a cat, so on. A representation that learns these concepts along the way is, of course, what a deep learning network does anyhow. So the qualities of a representation then are the representations should have 4 qualities. Be as informative as the data. The data, of course, has a lot of information in it. So we are losing information when we go to a representation. And so we need to retain as much of the information as possible, but be invariant to nuisance factors such as noise, that this is irrelevant to any task. So that is invariance. Be disentangled, that the particular representations capture different dimensionalities. And be simple and easy to work with, that we can work with them, maybe such as like providing an explanation. So we can give a quick explanation. That would be something easy to work with. For representation optimized to task, find trade-off between accuracy and complexity. So you might say, well, this is what is good for this task. There again, we have to trade off between, how much of accuracy are you getting and how complicated it is. There's no point in saying that the reason I classified it as a cat is because the pixels in positions 1538, 1836, and 1748 all had the same value. What value is such a feature, very complicated feature. So we want it to be less complex than that. Okay, so that brings us to a close on the chapter 15 of representation learning, which I believe is an extremely important chapter. And the next chapter is chapter 16, which is about structured probabilistic models. basically probabilistic graphical models. That's a classic topic. We'll cover that a bit because it keeps showing up when we go to generative models, where we use things like Boltzmann machine, so on. We've covered it a little bit, but we'll do a bit. Okay, I'm going to stop there. And do you have any questions? Let me ask Setu, do you have any question for me?
Oh, sir. Thank you.
Yeah. Okay, thanks, Setu. Anyone
Yes.
else?
Only 4 participants are there apart from we both.
Okay. All right, fine. Yeah, I put up this recording online, so hopefully they have a chance to look at it. Okay.
Yeah. Online is on Facebook or in
Yeah,
your website, sir?
today I enabled Facebook, so it should be on
Okay.
Facebook, but I also put it on YouTube. So you
Okay,
can
okay.
go to YouTube also. The slides are all
Yes.
up on my website. I also
Yeah,
have
yeah, that I have
I have
seen.
a link to the YouTube from the slides also. I've been putting the links
Okay, okay.
a few days
Okay,
after.
okay.
Okay.
Yes, sir.
All right.
Okay,
Have a
sir.
nice
Thank you,
day
sir.
and see you
Thank
on
you, sir.
Wednesday. Yeah.
Yes, sir. Sure, sir.
Okay.